All right, so here we're going to introduce the determinant of a matrix. All right, now before we get into that, we want to define what are called elementary matrices. All right, now I'm going to show the definition here from our textbook. Now, the elementary in that they are very basic, straightforward matrices. The definition, unfortunately, in the textbook looks incredibly jumbled here. So I'll show you what it looks like here, and then we'll try not to freak out over seeing the notation here because it is overwhelming. All right, so if we look at here, so the textbook defines the definition ELM, elementary matrices, and it has three different elementary matrices. All right. This has the first one where I does not equal J, then it has all of these definitions here, right? K is equal to I, L equal to J. Again, right? It's very overwhelming here, trying to look at all these subscripts, right? So this is kind of just a formal notation. So you could see here if you were for some reason trying to, program this into a program and you wanted to program what an elementary matrix would look like, you can work with the subscripts like this, right? What these elementary matrices are is that they represent the three types of row operations, right? So we'll illustrate this by a 3x3 matrices. So just to keep the size small, but just keep in mind this will apply to any size matrices here. All right, so here, let's see here. Okay, so here, talking about elementary matrices. Okay, and keep in mind that these are here to represent our row operations, right? So keep in mind we have three valid row operations, right? So the first row operations, right, we can swap rows. Two, we can multiply a row by a scalar. Which we'll call alpha. And then the third one is we could have, so here we could add alpha times a row, let's say I to row J. Okay, so those are our three basic, just our three row operations. Okay, now our elementary matrices set to set to write the row operations as matrix multiplication. Okay, so we can represent swapping rows by multiplying a matrix. Now, the idea behind this is that this will help us work with determinants, since the determinant is an operation on matrices. And if I can represent row operations through matrices, right, then I can calculate its determinant. Okay, all right. So here, the first one, so elementary matrix. All right. Okay, so here we're going to focus on square matrices here for our elementary matrices. All right. Okay. Actually, So our elementary matrices will be square matrices, but they can be applied for, since we're going to focus on left multiplication, right? Any matrices as long as the operations, the dimensions line up for the operations. Okay, so let's say, for example, we have a set of equations that has 3 equations. Excuse me. All right, and again, a reminder here, we have our identity matrix, which I use to really, the elementary matrices are variants on these identity matrix. So let's say here I wanted to swap rows 1 and 3. So the elementary matrix 1, 3 would look like this. Okay, so notice that this was just a swap of rows 1 and 3 in our elementary matrix. All right, and if you left multiply this by a matrix A, this has the equivalent row operation. Right? It swaps rows 1 and rows 3. Okay? All right. Now let's take a look at multiply. So here, if I want to multiply row 2 by, let's say, -1/2. So what that would look like would be like this. All right. Okay. And then that would be the equivalent row operation would be -1/2 R2. Okay. Now let's look at the third type of row operation. Let's say I wanted to multiply 3 by R1 added to R3, and now that becomes my new R3. Right, again, you multiply one row, excuse me, you add it to the other row, and that becomes the new row 3. Oops, excuse me, up here, this is 1. Okay, now if you wanted to represent this row operation, we have 1, 3, so this is the notation that we use, 3. What that looks like here it would look like this. Okay, all right, so notice that we still have that column there of the diagonal there of 1s, right? And now notice where the 3 is placed, right? It's in the first row. That's which row I multiply by. But now I'm adding it to the third row. That's why it shows up there. All right. Okay. Actually, excuse me, I got that flipped around here. Let me redo that here. If I think of the row operations, yeah, sorry. Since I'm adding it to the R3, the 3 is going to show up down here. Okay, my apologies there. Okay, so once again here we have 3 R1 plus R3, right? Whatever row that you're multiplying in, right? That's the column that you're going to be in here, right? And then the one that I'm adding to it would be R3, so it shows up in the third row there, right? So for example, let's say that we had here our matrix, right? That represents, let's say it's an augmented matrix. So let's say, how about 1, 2, 1. 3, 2, negative 1, negative 2, 4, and then actually here, let's start this off with and then 1, 0. Okay. All right. And let's say you wanted to go about reduce row doing the RREF and representing it with matrices, right? Now, the first thing I would like to do would be to multiply that first row by -1, or swapping row 1 and row 3, right? So let's just, again, I'm not going to go through the whole RREF, just some examples of how these elementary matrices work. All right, let's say I saw this and I said, oh, let me just divide through by -2. Well, the corresponding elementary matrix would be multiplied by -1/2 row 1, right? So the matrix here would be -1/2, 0, 0, 0, 1, 0, 0, 0, 1. All right, and again, the multiplication will always be on the left side. So here, let's do the matrix here, 2, 2, 4, 6, 2, -1. All right. -2, 4, 1, 0, -3, -3. All right, so if I do this, right, again, we would multiply -1/2 by -2. That would be 1, right, and then 0, 0, 0. So that would be only 1 here, and then if I move on here to the next one, -1/2 times 2, that gives me -1. All right, and then if I try to add everything else, all the other ones get zeroed out, right? And you start to see how this works, right? So -1, right? Still in the first row. Now in the third column, -1/2 times 4 is -2, and then plus the rest are 0, 0, 0. Okay, and then the last column, -6 multiplied by -1/2, -3, and then the rest gets zeroed out. All right, and now notice as you try to multiply the rest, right, it is untouched. All right, if we move on to the second row, first column, 0 times -2, 0, 1 times 2 is 2, and then 0 times 1, so we're just left with 2. Okay, and then again, moving on here, still second row, now in the second column, so 0 times 2 plus 1 times -1, -1, and then the other one is 0. All right, and then moving on here, 0 times 4, 0, 1 times -2, -2. All right, and then the other one, 0 times 6. Here, that's 0, 1 times 4 is 4. All right, plus 0, because 0 times 3 is 0. And you see that second row is untouched. And doing the third row multiplication, you see right away, you're at that. And you notice here that first row is exactly the row operation here that you wind up with is -1/2 R1, right? Represented by that elementary matrix. Okay. And now let's say you wanted to do the row operation -2 R1 plus R2, and that's going to be my R2. All right, so my elementary matrix -2. All right, so what that would look like if we're working in the second row, so this, all right, we don't want to change the first row. So we do want to change the second row by multiplying the first row by -2, right? And then adding it to the first row, to the second row, excuse me. So it would look something like this, right? And again here, right? So left multiply always. Okay. So notice as you start to do the multiplication across row 1 and all the columns here, you'll see those will just be untouched, right? If you look here, 1 times 1, 1, and then the other two terms 0 out, right? 1 times negative 1, negative 1, the rest of the terms 0 out. So we keep going here, negative 2, negative 3. All right, now here's where the work happens, right? We're in row 2. And now times row 1 here, or column 1, excuse me. So that would be negative 2 times 1 plus 2, and then the third one cancels out. So we get negative 2 plus 2, that's 0. All right, and now moving on to the next column, right? Again, negative 2 times negative 1 is 2, and then plus a negative 1. So we get positive 1. All right, and now moving on here, right, to the third column here. So negative 2 times negative 2 is 4 plus a negative 2. So that gives me 2. And then lastly here, negative 2 times negative 3 is positive 6 plus 4 equals to 10. And now the third row we see will remain untouched, right? 0 plus 0 plus 1, 0 plus 0 plus 0. Okay, and then here 0 plus 0 plus negative 3, and then negative 3 as well. Okay, but we see that second row is where we did our work, and that is equivalent row operation of negative twice row 1 plus R2. And we could see we get the exact same thing there. All right, so let's do one more. Let's just swap row 1 and row 3. All right, so if we want to swap row 1 and row 3, right, the corresponding elementary matrix would be this. All right, and now here, let's look at okay, and let's look at what happened as we start to multiply here. All right, and you could start almost seeing the operation here, right? First row, and then the first column here. So 0, 0, and then the last one would be 1, right? And you can start to see these are all just going to move up here, right? That's what that first row expansion is going to do, right? So we have 0 times 0, or excuse me, 0 times negative 1, 0, 0 times 1, 0. And then 1 times 0 is 0, so that one is 0, which is what we expected. And then moving on to the third one here, the first two elements are 0, and then the third one is negative 3. So that's the only thing there, 0 plus 0 plus a negative 3. And then lastly here along that fourth column, 0, 0, and then times 1 times negative 3 is negative 3. All right, and you see there, row 3 is now row 1. Second row, as you multiply this out, it remains untouched. So it's 0, 1, 2, 10. And I look at the third row here multiplying by the first column. So the only one that is left here is the first element. So 1 times 1, 1. Moving on to the second column, only get the first element, negative 1. And then the third column, again, only get that first element because the other two get zeroed out. Negative 2, negative 3. All right, there we go. All right, so that is how you represent the elementary matrices, or excuse me, how you present row operations using these elementary matrices. All right, so now all that here, a couple things about these elementary matrices, right? If you multiply them on the left, right, this is not going to work on the right. And even in this case, if you try the right, it's not defined. The operation, the multiplication is not defined. All right, but it'll only work for left operation to perform the row operations. Another thing is that all the elementary matrices, they are non-singular. Okay, so they are invertible, which makes sense, right? If you think of it, right? If these represent all the row operations to get me to reduced row echelon form, I should be able to go the other direction. In other words, the inverse of these, right? In order to retrieve the original matrix. All right, so a couple things here. Elementary matrices, two properties. One, the left multiplication represents row operations. And two, all, let's just call them EM, elementary matrices are non-singular. So I'll just present those two properties without proof. Elementary matrices. Okay. All right. So now to the determinant. All right. So first, the determinant. A couple things. The determinant is relevant or is applied to square matrices. Right. It's a function from square matrices. So the determinant is some kind of function from square matrices, so only n by n, onto scalar. So it's going to be real number, right? So when we take a determinant, the resulting value is a number. Okay? All right. Now, if we think of the very basic 1 by 1 matrix or a scalar, so the determinant of that is simply the value of the number. Okay. All right. And again, all right, if you look at the definition in the textbook, right, it has a very technical definition here. Okay, so here. Okay, so if you look here, all right, it starts with the determinant of a 1 by 1 is just the value of whatever the element is. Right, and then it goes into this matrix with size n greater than or equal to 2. Then it goes across this kind of expansion here. All right, now what we want to get from that is here that we want to be able to expand across really any row, right? This states here like the first row, but it really doesn't matter which row that we expand across here. So, oops. Okay. Now in the definition, it states to expand along row 1, and later we'll see that I can really expand across any row or column. Right, so it says expand along row 1, right, and then you get these sub matrices here. Now let's row 1. Okay, now instead of writing the theorem down, I'll just kind of work through an example here. Now, one thing that is going to be true here, and I'll just introduce it here. For a 2 by 2 matrix, all right, so we have 1 by 1, that's just a value here, but really the formula for 2 by 2 is nice and clean, where it's the AB minus CB. All right, and here, and actually instead of these brackets here, to show a determinant, we use the absolute value, right? So this is the determinant. So the determinant of any 2 by 2 matrix looks like this, right? Now, for any larger matrix that I want to expand, right? So that formula in the textbook, so boils down to this, right? So here I want to take a look at (3, 2, -1), 4, 1, 6, and -3, -1, 2. All right. So if we're going to expand across any row, one thing to keep in mind is that the signs always alternate. We start with plus, but then it goes to minus, plus, minus. Okay? All right. And if we expand across any column, which we can do as well, it'll be always start the first element, 1, 1 is plus, and then you alternate signs as you go. All right? And what we're going to do is we calculate a series of submatrices, right? As you can see, the number of operations kind of grows, right, as the matrix gets bigger in size, right? A 2 by 2, we have a nice formula here, but even at 3 by 3, we could see that it starts to get a little bit more involved here, right? So here's what the expansion would look like, all right? We start with the first row, right? And here I'll actually do first row, and then I'll choose like another column to show that it's not really going to matter here, right? I'm going to choose the first row here, and the first thing to do is, as I choose the row here, so here, what I'll do is, this is kind of like my pivot here. So that one is positive, so we start off with 3. Actually, here, let me switch numbers here. So it'll be 3. And I'll have the submatrix that I get by blocking out the first row and the first column. Okay, so if I do that, I'm left with this submatrix. 1, -1, 6, -1, 2. Okay. All right. And then from there, okay, so then from there, I move on to the next term. Right, so the next term, all right, again, I'm expanding across the first row. So my next term is -2. Now the submatrix here, right, I get by still blocking out the first row. This whole time I'm blocking out the first row. I'm using it as my coefficients, but now I block out that second column. And now my submatrix is the matrix 4, 6, -3, 2. All right, and now I'm back to being plus, but the number in that element, the third element in the first row, is -1. So we have our -1 here. And the submatrix I get there is from blocking out First row still, but now the third column. And we see the submatrix there is 4, 1, negative 3, negative 1. Okay, and now this expansion here is this called the cofactor expansion. Notice that the resulting submatrices are all 2 by 2. So I would be able to calculate the matrix, the determinant of the matrix, by using this above formula here. Right, so this becomes 3, 2, negative 1 here. So 2 minus a negative 6, so 2 plus 6. And then minus 2. Again, watch your signs as always here. 8 plus 18. Oh my God. And then plus or minus 1. Here we have negative 4 plus 3. Okay, and now simplify. All right, 3 times 8. This is what, 26. And then minus 1, negative 1. So this becomes 24 minus 52 plus 1. So now we get 27, or negative 27. Okay, so that is the determinant of the matrix. Right now, again, if you started off with a 4 by 4 matrix, you'll do the same expansion. The only thing there is that when you do the expansion the first time around, right, or expand across that first row, your resulting matrices aren't 2 by 2s, they're 3 by 3s. So you would have nested in there, you would have to do this exact same operation where it was a 3 by 3 3 more times. Right, so as you can see, right, to do this by hand with anything higher than a 3 by 3 is a lot of calculations. Okay, but again, here is how you would do it. Here's what the process looks like. And notice I said that it doesn't matter where you expand it from. You could choose any row, you could choose any column. Really, you just have to keep track of your signs. They're always alternating, right? With the first row, the element in the first row, first column being positive, and then expanding out their minus, plus, etc. Right, so let's do that one more time just to show you that we will arrive at the same conclusion here. So let's see, 3, 2, negative 1. Four, 1, 6. And then here, negative 3, negative 1, 2. Oops. Okay. And then here, I want to expand across that second. I want to expand across that second column. All right. The operation remains the same. I'm just expanding over a different column here. All right. So here, and again, all I have to do is remember keep track of my signs here. All right. So the way that would work is I'll start off with a negative 2. Right. And again, the way this works here is my 2 is in the first row, second column. So if I kind of cross out everything in row 1 and everything in column 2, the submatrix I'm left with is 4, 6, negative 3, 2. All right, and then instead of moving across along the row, I'm moving along the column. So if I start off negative, the next one would be positive, in this case 1. Now my submatrix here will come from, again, I'm still in that second column, so crossing that one out. Again, I'm going to use all those coefficients, so I only use them here. And now I'm in the second row, so I cross out the second row. So my submatrix becomes 3, -1, -3, 2. All right. And then lastly here, I'm in -1, so minus, plus, minus. So we're at a minus, a -1. And the resulting submatrix, here again, I'll do this one so you could see it. 3, -1, 4, 6. Okay. And then doing the determinant here. Right now, once it's 2 by 2, then it's just right across here, 8 plus 18 plus 1, 6 plus 4, and then plus 1. We got 18 plus 5. So here we get -2, 26, plus 10, plus 23. So we get 33. Up here. Six minus 3. Not sure where I was going there. Let me double check all my work now. So 8 plus 18, -2 here. Okay. 3, 6 plus 3, but minus. Okay. And then here, 18. 5, oh my God, 18 plus 4, 22. All right, so we get minus 52 plus 25 and -27, which is exactly what I got up here. Okay, and just by going down the second row. So this expansion, cofactor expansion, it doesn't matter where you decide to do it. Just keep track of your signs. Remember, always alternating, right? Think of it like a checkerboard here. Okay.